Good afternoon, everyone. Let's start. In the previous class, I showed that Huffman codes are optimal. So among all prefix-free codes, the Huffman codes are the ones which achieve the minimum expected length. There could be other codes which achieve the same expected length, but no other prefix-free code can achieve an expected length less than that of the Huffman codes. Okay. So recall that the proof was using these properties of prefix-free codes. We assume that for every optimal prefix-free code, we can find optimal. So every prefix-free code, we can always get an optimal code which satisfies three properties. And using these three properties, we obtain bounds on the expected length of an optimal prefix-free code. So remember that we looked at the proof was via induction. We know that Huffman codes are optimal for sources having only two symbols. The alphabet is of size 2. And then we extended this using the induction argument to general M symbols. Any probability mass function on M symbols. We assume that Huffman codes are optimal for all sources up to M-1 symbols. And using sort of the three properties, we showed that no matter what happens, Huffman codes are also going to be optimal for sources on M symbols. All right. So we connected the expected length of the optimal code on M symbols with a derived code, with a shortened code on M-1 symbols. And similarly, we also obtained bounds on, or we derived an expression for the expected length for the Huffman code on M symbols with the Huffman code on M-1 symbols, right, for the merged source. And then we just looked at these two equations together, subtracted one from the other, and obtained an expression connecting the two. And we then noted that since Huffman codes are optimal on M-1 symbols, this quantity is always less than or equal to 0, which means that this quantity must always be less than or equal to 0. And the only way that can happen is that these two quantities are equal, and therefore the difference is equal to 0. Okay. Any questions? Any questions? Okay. Now, well, so we've designed. We know how to design Huffman codes, and we know that Huffman codes are optimal, right? So then now you may ask, okay, so what is left to be done? We know exactly what the best codes are for any given source. We know how to construct them, and they seem to be efficient. So is that the end of source coding? Well, the answer is no, and for that we go back to our original discussion on Symbolwise versus block source coding. So let's take the example of a sequence. After all, we're not interested in compressing just single symbols. We're interested in compressing long sequences of symbols. So again, let us assume that we have a sequence xn, which is IID distributed according to some known distribution px. Okay, so xn is just x1, x2, x3, so on up to xn. Right. So how would you compress this sequence? Well, you know px. Each component is distributed according to px. So what would you do? You would design the Huffman code for corresponding to px. For just to be concrete, let us assume that the source alphabet is let us say A, B, C, let's assume that the probability mass function is, say, half 0.3, 0.2. Okay, so this is our source. Now what do we have? So we're given a particular sequence, right? Let us say A, B, A, C, B, A, C, B, and so on. So we have this particular sequence. This is our xn, this is our source sequence. And maybe we have calculated the frequency, either we are given the PMF beforehand, or maybe we have estimated this probability mass function by computing the frequency of occurrence of A, frequency of occurrence of B, frequency of occurrence of C. Okay, so can someone quickly tell me what the Huffman code for this PMF will look like? Can someone give me a Huffman code?
A equal to 0.
Can you please repeat? There's a lot of noise.
A 0.
Okay, 0.
Then 1 0 1 1.
Okay, 1 0 1 1. Fine. So this is going to be a Huffman code for this particular source. Okay, so what would be the encoding of xn? So if I use the Huffman code to compress this particular sequence, uh, well, A is going to be replaced with 0, B is going to be replaced with 1 0, A is 0, A is 0, A is 0, C is 1 1, B is 1 0, A is 0, C is 1 1, B is 1 0, and so on. Right? So the compressed sequence is going to look like this. It's just a sequence of bits. I've just replaced each A with a 0, B with 1 0, and C with 1 1. Okay? And how would you decompress? You again start going from the left. You have the corresponding Huffman tree, which looks like this. So this is A, 0 1, 0 1, B, and C. Right, so we start reading from the left. The first bit is a 0, so therefore the first symbol is an A. So this is going to be A, and then you see that the next bit is 1. You again go back to the root. You see that the first bit is a 1, and the second bit is a 0, so it's a B. You go back to the root. The first bit is a 0, so it is an A. And similarly, you keep doing the same thing. A, this is going to be a C, this is going to be a B, this is A, this is C, this is B. Okay, so you know how to encode and decode if you're given a particular source. Okay. So what is going to be the expected length? Can someone compute? Expectation of L of X is summation over all A, P of A, maybe it's not the right notation. Let's use X, little x, L of X, right? What is the expected length going to be? Okay, so 1.5 bits. Okay, and what is the entropy going to be? Since we know that this is the best, this is sort of the lower bound for any source. This is the lower bound on the compressed length, and the best that you can achieve is entropy. What will the entropy be equal to?
1.48.
Okay, so 1.48 bits. All right, that's fine. Now let us look at the following case. Since I have a sequence of length n, what will be, so suppose that n is let us say 10,000. So that it's a sequence of length 10,000. What is going to be the compressed length for the entire sequence? So the expected compressed length for the sequence xn. What would this be? So remember, the total compressed length is just the sum of the compressed lengths for each of the symbols.
N into 1.5.
Exactly. So it's going to be n into 1.5. So it is expectation summation I equal to 1 to n L of xi, which is again by the linearity of expectation. This is expectation of L of xi, which is just n into expectation L of x, which is 1.5 n. In this case, it is going to be what? 15,000. Okay. But what is the entropy? Assuming that the sequence is IID, what is the entropy of xn?
N into h of x 14802.
Correct. So it's going to be, since it's IID, the entropy of xn is n times h of x. So that is going to be 14,800 bits. Okay. So clearly there's a gap. The entropy of the sequence is 14,800 bits, whereas the compressed length that we can achieve using this particular code, the Huffman code, is 15,000 bits. So you're off by 200 bits. Well, this is okay if the sequence is small, but then now if the sequence is, so this would correspond to what? Just a 10 kilobyte file. But let's say that the sequence was 1 gigabyte long, and you use this particular technique, you're not doing terribly well because you're off by a huge factor. So the question is, can you do better? Can you at least improve over this? Right? Well, the one approach is, now instead of taking each of these sequences, like instead of compressing this symbol by symbol, I can group together blocks of symbols. So I have xn, which is A, B, is it? Yeah, A, B, A, C, A, C, whatever, B, A, B, C, and so on. I can group this into blocks of maybe 2 symbols each, right? So now I have a new sequence. Let me call it Y. The length of the sequence is n by 2, which is Y1, Y2, Y3, and so on. So each xi came from the alphabet script x. Each yi is a pair of symbols. It's the pair of consecutive symbols. So each yi is basically what it is, x 2i minus 1 to I. Sorry, x 2i minus 1, comma, x 2i.
Sir,
Yes.
this can you explain like once like yi belongs to alphabet square?
Yeah, so by alphabet square, I mean all possible pairs of symbols from X. Right? So in this case, X was A, B, C. Now I'm taking pairs of symbols. So this is one symbol in, this is Y1, this is Y2, this is Y3, this is Y4, and so on. So each Yi can take values in either AA, AB, AC, BA, BB, BC, CA, CB, CC. Right?
Yes, sir. So that is for Y. Okay, yi belongs to this alphabet square you've taken.
Yes,
This and xi belongs to this alphabet only you've written, no sir.
correct.
So this xn equal to ab, aa, cb like that you
Mhm.
mentioned, and like this xi belongs to this the alphabet, no sir. So it will be
Correct.
counted.
So this
This
is a
AB.
sequence of length n. Right? The sequence, remember that the sequence is still the same. I'm not changing the sequence. It is still AB, AA, CB, AB, AC, and so on. But the only thing I'm changing is what the alphabet is. I can view the same sequence as as a sequence of symbols from A, B, C, or I can also view it as a sequence of symbols from this set, right? So think about it in the following way. If I give you let's say an English sentence, you can treat it as a sequence uh, of letters from the English alphabet, or you can also treat it as a sequence of words, valid English words, right? But the sentence still remains the same, right? What you want to compress, the original source has not changed. The only thing that has changed is how we are viewing the source, as a sequence of letters or as a sequence of words.
Yes, I got it.
Uh,
So where I got confused was like xn equal to ab, it's in pairs, no? So
Yeah, so this pairs and whatever, I've just drawn this to understand, but what you have is just, you don't have any of these commas or anything. It's just a sequence of symbols, right?
yes, sir. So in xn we are just taking individual, and in y n by 2 we are viewing it as a pair.
Exactly, you're just viewing it differently.
Okay, sir. Yeah, got it. Thank you.
So I'm sort of grouping symbols before compression. That's it. Okay. So the sequence still remains the same. I've not changed the sequence. The source is identical. Nothing has changed. I'm only changing the alphabet, the way I view the sequence. I can view this as a sequence of length n, with each symbol coming from this alphabet, or I can view it as a sequence of length n by 2 with, with symbols coming from this particular alphabet. Of course, now the alphabet size has increased, uh, and of course the distribution has also increased, right? So what is py of AA going to be?
Px of A into Px of C.
Exactly. So px of A into px of A, and so on. Right? So similarly, you can calculate the probabilities for each of these. Now you can construct the Huffman code for this new source for py, and then compress the sequence, the original sequence that you had, using this new Huffman code. But this is a Huffman code not designed for px, but rather for py. Right? You have, of course, there's an implicit assumption that I'm making here, that the sequence has even length, right? Because otherwise this yn by 2 doesn't really make sense. So the assumption is that n is even. That's okay. It's not a I'm not losing out much by making this particular assumption. If you want, I can just add another dummy symbol at the end. But now I'm getting something better, right? So I'm compressing according to this new distribution py. So I design the Huffman code for py, and then proceed. Right? I compress it using the new Huffman code, but designed for py. Whereas in the earlier case, I had compressed it using the Huffman code designed for px. Okay. Now the question is, can this do better? All right. It turns out that yes, it can do better. And here's a simpler example to see why designing Huffman code for blocks, for larger blocks, can do better than compressing it symbol by symbol. So take the following example. Suppose that the source that you have is binary. Xn is a sequence of bits okay, and the probabilities are as follows. Px of 0 is let us say 0.2, or yeah, sure, let's say 0.2, and Px of 1 is 0.8. Okay. Now, if I design the Huffman code for this particular source, what would be the compressed length for Xn? What would be the Huffman code for this? Yeah,
So
sorry.
0, 1, 0, 1, 0.01.
Exactly. So, well, the Huffman code is basically the same thing. So, the compressed length, if I use the Huffman code for px, this would still be equal to n. Basically, I'm not obtaining any compression. Okay. Now, what do I do? So, does this mean that this is the best that I can do? No, I can use the same approach. I can group pairs of symbols. Right? I can group pairs of symbols and now design a Huffman code for the new alphabet. So I view this. So yi comes from 0, 0, 0, 1, 1, 0, 1, 1. My alphabet has size 2. Sorry, the alphabet has size 4. What are the probabilities?
0.04, 0.16, 0.16, 0.64.
Exactly. 0.6.64. Right? Okay, that's good. So what will the Huffman code be? Maybe you can do it 0.64, 0.16, 0.16, and 0.04. So you would merge these two, get 0.2, and then you would merge these two, get 0. Sorry. 36, and then finally you would merge these two at 1. Right? So here's a code word assignment. I can assign this code word 0. So 0, 0 gets replaced with the code word 0, 1, 1, 0, 1, 1. The code words for 0, 1, 0, 1. So 0, 0.
Sir, I think the order is wrong. Like, 1, 1 should be 0.
1, 1 should be. Okay, sorry. So 1, 1 is 0.64, 0, 0 is 0.04. So 0, 0 gets the code word for 0, 0 is 1, 1, 1. The code word for 1, 0 would be 110. The code word for 01 would be 10, and the code word for 11 would be just the bit 0. Okay, fine. So maybe we've made some improvement now. What would be the expected length? So the lengths are 3, 3, 2, 1, and the probabilities are the same. So 0.64, 0.16, 0.16, 0.04.
So 1.56.
1.56, is it?
Yes, sir.
Sorry, it should be n by 2 into expectation of L of. Sorry, let me. I'm viewing it as a sequence of length n by 2 and of y n by 2. So it would be 1.56, is it? Okay, and when 1.56 into n divided by 2. So what is it in terms of n? Can you simplify?
7,800.
Okay, so 0.78, right? In general, for any n.
Okay, yep.
Yeah, thanks. Okay, so now it's the same sequence. Remember, it's the same sequence of length n. In the earlier case, I couldn't do anything. If I did it symbol by symbol, then the expected length was n bits. But now I've brought it down from n bits to 0.78 n bits. So that's good. So if n is large, then I've substantially improved over no compression, right? So now this is a good strategy. If the alphabet size is small, then maybe you should group together symbols so that you have a slightly larger alphabet size, so that increases the complexity of designing the code, but then you do much better in terms of the compressed length. Okay, so that's good. So now you may think, okay, why only group pairs of symbols? You could group 3 symbols together or 4 symbols together, right? That's potentially what you could do. So in general, group, I don't know, whatever, B symbols together. And maybe design the Huffman code for the sequence of length B. Right? So that's much better. In fact, you can exactly compute what you can achieve, right? So if you did if you did this, then so you design the Huffman code essentially for XB, for sequences of B symbols, and you know that the expected length for a sequence of B symbols is going to be the entropy of XB. It's going to be less than or equal to entropy of XB plus 1 bits, where it is greater than or equal to entropy bits. Correct. So now if
Sir?
Yes.
Sir, but won't that increase the computational complexity of calculating?
Exactly. That is true. So you're increasing the computational complexity, no doubt. But the gain that you're obtaining is in terms of the compressed length. So
Okay.
the computational complexity is proportional to the size of your alphabet So it can grow exponentially with, so clearly as you increase B, the size of the alphabet increases exponentially in B. All right, so the size of xb is the size of x whole raised to the b. So this is increasing exponentially in B. So larger B, of course, may improve the expected length, but there is this price that you have to pay in terms of computational complexity of encoding, decoding, as well as designing the code itself. Right. So, but you're also obtaining some gains, right? So if you compress a sequence of n symbols, where n is some constant times b, if n is some constant times b, then the expected compression length is now c times h of xb, but less than or equal to c times h of xb plus 1. If this is an IID sequence, if xn is IID, then c times h of xb is just the same as n times h of x, which is n times h of x plus c. Okay, so remember that c is equal to n by b, so it basically grows as n by b. So this is good, because now if I increase b, then the gap to entropy keeps decreasing, right? It's inversely proportional to b. So expectation of L of xn minus the entropy, it is at most n over p. So if I increase b, then I can get closer and closer to optimality, right? For the long sequence. So clearly grouping together symbols is good in terms of the compressed length, but it is bad in terms of computational complexity, right? So if n is very, very large, then if you only want to get, let's say I want to get to within a constant gap away from the entropy, right? So I want expectation of L of xn minus n times h of x to be at most a constant, independent of n. Then it would mean that b should also grow as a constant independent of n, and that is not, it's not practical, because the computational complexity would grow exponentially in the size of the alphabet, right? So it will grow exponentially in n. So clearly Huffman codes are good for certain sources. They're quick, they're easy to implement, and of course they're optimal. But then if you have long sequences, then maybe Huffman codes are not the best that you can do. Is there something better that you can do in order to in order to sort of encode a sequence of IID symbols? Okay, and that is what we'll try to do now. Okay, so far, are there any questions?
Sir,
Yes.
so as we increase the alphabet size, like initially we started with a pair and then like a triplet and like that, we keep increasing, then the size will decrease. So, but we should have some balance between this like expected length and the computational complexity, sir. So
Correct.
is there something like that, like optimal grouping?
Optimal. Well, that depends on how much computational complexity you can use. But now well, what you're heading towards is sort of a different approach. Well, you can, of course, that's a valid question to ask. What is the balance? What is the best choice of B? So if n is very large, what is the best choice of B, which gives you the sweet spot in the trade-off between computational complexity and the compressed length? There's no good answer to that because, of course, it could depend on your application. If computational complexity is more important to you, and compressed length not so much, then you choose a small b. But then if you have very stringent requirements on the compressed length and computational complexity is okay, then you can choose a slightly larger b. The goal, however, is to design a compression scheme which has low complexity, and secondly, if you have a long sequence, it still gets you close to n times the entropy, and this gap does not increase with n. If b is, let's say, a constant independent of n, then this gap to entropy is also increases with n. And ideally, we want to design a scheme for which this quantity, this difference, does not increase with n. So it's always a constant irrespective of what the source is. Is that clear?
Yes, thank you.
Yeah. So this is definitely one approach that one might use. But now, but there's of course this cost. You have to pay a price in terms of the computational complexity, and that's not something that people are generally willing to pay, because as B grows larger, the computational complexity grows exponentially with B, and that is too much. Very quickly, the computational complexity can explode. Okay, so what we want to do now is to use a completely different approach to designing a good efficient compressor. Okay, so Huffman codes are optimal, but they're maybe not the best if you want to encode sequences of symbols. If you want to encode individual symbols, then they're good. Okay. Okay. So before we proceed, we'll have a quick quiz. I will sign the quiz on Google Classroom. I have assigned it on Google Classroom, but here is the link in the chat box. You can take 3-4 minutes to answer this. Is everyone done?
So just 1 minute.
Maybe 1 more minute. All done? Anyone yet to submit the response? Anyone yet to submit? Okay, so I will stop accepting responses now. Right, so there were two questions. One of the questions was that if you have a source with entropy, I think whatever 2.3 bits, then what can be the expected length of a Huffman code designed for this? You know that the expected length has to be between h of x. It should be greater than or equal to h of x. And the Huffman code also achieves an expected length less than or equal to h of x plus 1 bits. So I think there was only one option, which was 2.5 bits or something. All the other options were either less than h of x or greater than h of x plus 1 bits. The other question was which of the following can be a valid Huffman code? The options were the first one was 0, 0, 0, 0, 0, I think 1, 0, 1, 1. This is not a Huffman code because this is not prefix free. There's another option 0, 1, 1, 0, 1, 1, 1. 0, 1, 1, 1. This is also not a Huffman code. Because it cannot be obtained by merging symbols. So if you draw the tree, you can immediately realize that this code can never be optimal because this is a shorter code. You can assign shorter code words to two of the symbols. So this is not a Huffman code. The others, so one was just 0, 1. This is a Huffman code. The other option was 0, 0, 0, 1, 1, 0, 1, 1. This is also a Huffman code. For example, you can try to design the Huffman code for the following source: 1/4, 1/4, 1/4, 1/4. So if you try to obtain the Huffman code for this distribution, you'll get that this is the Huffman code. Okay. All right. So let's continue. So we've seen that Huffman codes are not perhaps the best if you want to encode long sequences of, long IID sequences of symbols. Right? There's this trade-off. You can't efficiently encode and still get very close to the entropy. So what do we do? Now we're going to look at a different code, the Shannon-Fano-Elias code. When you look at it in the beginning, it may seem that this is worse than the Huffman code. In fact, for individual symbols, the Shannon-Fano-Elias code is worse than the Huffman code. It's even worse than the Shannon code. But as we'll see, there's a very efficient way of encoding this, and this will sort of pave the way towards another class of codes called arithmetic codes, which lets you encode sequences of symbols. Okay, so we'll do it step by step. So let's see what is the Shannon-Fano-Elias code. The approach is the following. So you are given, let us say, a sequence of symbols. Without loss of generality, let us assume that the alphabet is 1, 2, 3 up to m. So you have m symbols in the alphabet. You have one symbol. So x belongs to this particular alphabet, and there is a distribution. So px is known. And we want to design a prefix-free code. Now, given a particular probability mass function, what is the cumulative distribution function? How do you compute the CDF, or the cumulative distribution function, for any x? Yes?
For the discrete one, we take summation.
Okay, the summation over what? Okay, what is inside the summation?
So the probability of PDF.
Okay, so it's a P of A, and what is the summation over?
A equal to 1 to x.
A equal to 1 to x, or summation over all possible A less than or equal to x. Correct? And the CDF is defined for all real values, not necessarily symbols which belong to this particular set. Right? So if I have a PMF which looks something like this, so 1, 2, 3, 4. So if the PMF looks something like this, the x-axis is x, the y-axis is p of x, then the CDF is going to be a non-decreasing function. So there's a jump at 1, there's another jump at 2, there's another jump at 3, and there's another jump at 4. And the value of the what is going to be the value of the CDF at this point?
One.
It's going to be 1 and 0 for all x less than or equal to 1. right? So this is the CDF for a general probability mass function. Now I'm going to define a modified CDF. We call it M CDF. I will denote it as f bar of x. So it is the summation overall a less than x px of a plus p of x by 2. Okay, so this is for x in the alphabet. All right. So this is what I define as the modified CDF. This is again defined for only x in the alphabet, whereas the CDF is something that I am defining for all points. Okay. So what can you say about the modified CDF? What values can the modified CDF take? It's always non-negative and it is at most 1, right? So for all x, in fact, for all x in x, you can improve the upper bound. So it is, you can improve both the upper bound and the lower bound. What is the smallest value of the modified CDF? So when is f bar of x the smallest for what value of x? Sorry.
Like when x is symbol correspond to the least probability.
Well, I'm just saying. I'm not ordering the probabilities or anything, right? I'm saying that that you have p of 1, p of 2, p of 3, and so on. It is already ordered according to something. Doesn't matter how it is ordered, but the CDF is defined with respect to x, right? So it is the smallest when x is equal to 1, right? Correct? Because f bar of 1 is p of 1 by 2, f bar of 2 is p of 1 plus p of 2 by 2, and so on, which is larger. And what is the maximum value of f bar of x? It is strictly less than 1. It is maximized when x is equal to m. So a less than m, p of a plus p of m by 2, which is equal to 1 minus p of m by 2. Right? So f bar of x is going to be some number strictly between 0 and 1, and in fact it is going to be greater than or equal to p of 1 by 2 and less than or equal to 1 minus p of m by 2. So here is a scheme. Okay, we'll see the properties and everything in the next class, but here's the compression scheme, or here is the encoding. For any x, compute f bar of x in binary. Okay, so it's a number between 0 and 1. So you can write f bar of x to be 0.8 in binary, let's say B1, B2, B3, B4, and so on. So this is the binary representation of f bar of x. And you truncate up to L of x bits. So basically, you just look at B1, B2, B3 up to BL of x, where what is L of x? L of x is going to be the seal of log 1 over p of x plus 1 bit. Okay. So the overall scheme is the following. You compute f bar of x for each of the symbols 1, 2, 3, 4 up to m, and you compute this in binary. So compute the binary representation. So maybe the binary representation is 0.0.11010101, and so on. And then you compute L of x, which is log 1 over p of x plus 1 bits, and maybe L of x is equal to 4. So you just take the first 4 bits of this binary representation, and that is going to be your code word. So 1101 is going to be the code word for a particular symbol x. All right. So this is something I'm giving you an algorithm. So in the next class, we'll see an example, and then we'll show that in general, this approach always gives you a prefix-free code, and we'll also obtain an upper bound on the expected length of this particular code. Okay. So we'll see that we can encode and decode, we can construct the code tree for this particular code, and so on. All right. Any questions? Any questions? Okay, so if not, then we'll meet in class tomorrow.
Sir,
Yes.
this L of x equal to 4, we're getting now. So this is the probability,
So
this
it's
p of
using
x.
this.
So yeah, the del of x we get from this p of x. That p of x is corresponding to some symbol.
So for example, assume that x equal to 2, then you compute f bar of 2, and you compute f bar of 2, and then you compute L of 2. Maybe L of 2 is 4 bits, and f bar of 2 is equal to this, and you just truncate this up to 4 bits.
Okay, thank you.
Okay, we'll see an example in the next class, which will hopefully make things more clear.